It is a great honor for me to introduce Roza Leikin. Roza is a professor at and the dean of the Faculty of Education at the University of Haifa in Israel. Additionally, she is the predecessor of Marianne Nolte as the president of the MCG. Roza is a highly respected researcher who is famous for introducing multiple solution tasks to the field of mathematical creativity. She's also famous for very passionately discussing about her research, which shows how much she loves what she is doing. Roza, we are lucky that you took the time to speak at this symposium. The stage is yours.
Thank you very much. This is Benjamin. This is the best introduction I ever had. Thank you very much. So I will share with you the screen. I'm allowed, yes. And I will start with confessing that when I was thinking about the title of this, can I do? Yes. When I was thinking about the title of the seminar, I was puzzled. What does it mean, posing problems for gifted? What do you mean in this title? And in a minute, I will tell you about what I was thinking the possibilities are. And then also I have to confess that I am not a fan of problem posing as a didactical tool for mathematics classroom on a regular basis, but I think it's a perfect tool for gifted. So starting from here, problem posing for gifted, it raises a lot of questions. Do I mean that we as researchers or mathematicians or as mathematics educators and instructional designers write problems for students? I usually thought about problem posing as a different kind of activity, as an activity which is directed as a given task to create a problem, not as a natural activity of a mathematician or not as a natural activity of people who just doing this and enjoying this thing. Now, another thing that I was thinking, who is the gifted? For many times are talking about gifted students in very different meanings. We are not precise in definition who are the gifted. Also, when we are talking about problem posing, what is the level of complexity of posed problems? How do we think about it? And if this is problem posing for gifted, to allow gifted to solve problems, are those problems complex at a continuum of complexity, or this is a different type of mathematical task that we have to design for mathematically gifted? Then for which goals we're designing those tasks? And probably the previous questions that I raised depend on the frameworks, for whom exactly we're designing those tasks, for gifted in mathematical Olympiads, or in special classes for gifted, which Boris yesterday said that we have classes for gifted who are generally gifted, not necessarily mathematically gifted, or those for higher level mathematical classes, or for heterogeneous classes in which gifted are studying with other students, or those tasks that we create for teacher education. And also, what will be the use of those tasks? Will it be training or examination or at Olympiads or competitions? Then is it a research tool for characterization of gifted? Is it instructional tool or tool for teacher education? Is activity of problem posing itself will be instructional tool or tool for teacher education, or we're creating problems to teach students or teachers to solve problems? Are those tasks created for identification or evaluation of students, or we are willing to distinguish between mathematical expertise and mathematical creativity? So I just marked in color several things that I will touch on them during my presentation. And I want to stress that for me, all the questions that I raised now are truly research questions that I'm trying to apply in different kinds of research. And when we are talking about the level of complexity, then I'm using the framework for the level of varying level of mathematical challenge with conceptual characteristics of problem tasks, instructional settings, social mathematical norms, and all these will be relative to students' mathematical potential, the level of knowledge, level of creativity, or level of skills. So what I will be talking today about is openness, mainly about openness, insight, conceptual density of the task, and exploration. And also I will put an emphasis on technological tools in problem posing. I will start with MathSki project, and I had to, Boris yesterday mentioned that we have a philanthropic foundation in Israel, Trump Family Foundation. It's not American Trump, which everybody knows. It's Jewish Trump. So they are investing a lot of money in mathematics and science education in Israel. And I'm lucky to have several projects with them. I think I have now 6 projects that I'm doing with them. The MathSki project, what you hear is MathSki. We're opening mathematical tasks. We're creating open tasks for students. And based on all the literature, why open tasks are so important, and some research which was very famous with the group of Verschaffel and his colleagues in 1990s on open tasks. You probably remember the birthday party problem and buses problems, where the answers were open and students were shocked by the fact that they have to implement some realistic reasoning in solving the tasks. So we are now implementing those tasks in classes, and we had a huge development of such tasks in classes. So we also use the framework for classification of open tasks as open start tasks, and those are multiple solution tasks that Benjamin mentioned. Open-ended task, which has multiple solution outcomes, combined open-end and open start tasks, among which investigation tasks and problem posing tasks, meaning that you can go at the investigation task in different directions and you can arrive at different solutions, and the same for problem posing, when you can start it in different direction, posing different tasks and have different problem posing outcomes. So why problem posing, why open problems are so important, and this posing open problems for students actually coming to some very good results, because teachers usually are excited about problems that we suggest. First of all, it applies to different levels of students, and students can produce different number of solutions, and I will relate to this number of solutions as a critical issue. But anybody in the classroom, when they are working, in a minute I will show you the examples, and everybody in the classroom can be involved in this, engaged in this activity, and can be very active. When they solve open problems, they can also solve them in different ways. It requires from solvers mental flexibility and inhibition. It has a bigger number of concepts and theorems that they have to use, at least in multiple solution tasks. and mathematical connections, which are naturally occurring when students solving open tasks. So what can we do with teachers? And how can we teach teachers to teach those open tasks? So I will show you one study when we introduced to teachers math key problems, and teachers were asked to post open tasks using textbook tasks. So the paper is now published in ESM, and you can find the more details. I will show you several examples of tasks posed by the teachers. So one task is multiple solution task. A teacher takes a regular textbook task. A, B, C, D is a parallelogram. A, F, and C, E are bisectors. The point F and point E are on the diagonal BD, and they have to prove AF equals CE. This is a regular textbook task. And all the teacher does, she writes, solve the following problem in as many ways as possible. Very easy way to open task, but the requirement was solve, if you ask to solve problem in many ways, then present those solutions. So what we realized, the teachers have to solve at least 5-6 problems till they find something that they can find in several, they can solve in several ways. So you can see that the teacher who suggested to solve this problem in different ways suggested 5 different solutions. I'm not going, it's a very easy problem, so I'm not going to discuss those solutions, but she presented different solutions for this problem. Multiple outcome task, and I will return to this task a little bit later, but regular problem, movement problem. 2 friends, this is an open task which was formulated by the teacher. 2 friends are going along the same road. The distance between them, and I chose very simple tasks so you can follow what I'm doing here. The distance between them is 18 kilometers. The speed of the first friend is 5 kilometers per hour, and the speed of the other 7. What will be the distance along the road between the friends in 1 hour? So what she did, she just removed the direction of movement. She thought, okay, and it was a surprise for us. Instead of saying they are going one in front of the other, in the same direction, in different directions, she removed the information about the direction. And then there were 4 different solutions. When 2 cars, and I want to show you, we use this task in our project. Let me show you the applet I prepared. I'm sorry, I'm stopping the sharing, and I will share again the applet. So you can, excuse me. So I will share with you the applet. And you can see that we use in our project following this problem formulated by the teacher, we formulated something else with cars. So what we did, we presented to students cars, and they can change the direction. Can you see this? Just mark me the, okay. So students can change the direction and ask the cars to move, so they can see the first movement. They can change the direction of the red car and then see another situation. The cars are moving in the same direction. So we're supporting students with this possibility to see different situations in which they can have different answers. I return to my PowerPoint. Share. Okay, So this, you can see that when we ask teachers to formulate those problems, we also use the problems the teachers formulated further in the project. And then the next problem was the sorting task. I will not stop on it, but instead of saying that find parabolas for which you have the minimal point of vertex, the vertex is minimal point for the parabola for function, just find criteria for sorting the parabolas and then make groups of parabolas. So the teachers here have themselves find criteria for not just teachers, students. It's actually a problem which is posed for students. So if I think about this problem sorting task as requiring both activation, much bigger activation of working memory, and also flexibility when moving from criteria to criteria, and also inhibition, starting thinking from one criteria and then suggesting another. So this is much richer problem. And if you think about gifted are coming with criteria that other students are not thinking about, and they feel with this very good. Okay, so we were at sorting task, and then there are investigation tasks. I will talk about investigations a little bit later, but you can see the teachers were posing those problems, and we analyzed which problems they posed. And it's not a surprise that most of the teachers, at least at least 50%, about 50% of problems posed by the teachers were of the kind of multiple solution task, when they just require to solve problem in different ways. And multiple outcomes were in 34%, and most of them were by reducing conditions, some of them by changing the content or contents, and some by requiring generalization. And investigation tasks were posed by requiring generalization or by reducing conditions. It's also very natural. And sorting tasks were posed in 91% by reducing conditions, though there were only 11 of 109 tasks that we received from teachers posed of sorting tasks. Now, what was also interesting, we analyzed how much teachers familiar with open task, enjoy open task, posing open task, find it difficult or find open task difficult for students. So you can see that actually this is effect of the type of open tasks and familiarity. We see that teachers much more familiar with multiple solution tasks and investigation tasks than with sorting tasks. This explains very naturally why it was less, we got less sorting tasks. And also what was interesting, that familiarity with using open task and teaching was only for multiple solution tasks. So we have a lot of work to introduce multiple outcomes tasks to the classroom. Now, as I said, that I want to zoom in the two friends tasks. And this is the initial task. Two friends are going along the same road. The distance between them is 18 kilometers. The speed as I told you, and they are going in the same direction. So this is the one answer task, one solution. And then this teacher just removed the condition of going in the same direction, and she received 4 solutions. But saying the truth, she didn't say that they are going along the road. This is our addition when we wrote the paper, where I realized that the solution, there are infinite number of solutions if you remove this along the road. Okay, and then I want to show this is infinite number of solutions, but you receive this in equation. Now, how can we see it? And I don't have applet for this. Along the road have to be removed here, I'm sorry. So 2 vehicles I showed you for the first problem, and now along the road I remove. And we have another applet here that I designed today to show you, but actually if you look on this figure, let me show you how it works when we work with teachers. So I stop sharing and I'm going to GSP file. Just a minute, I'm sorry. Here it is. So I will share with you this file. So what we explained to students, where these 2 friends were at the beginning. There were these 2 points, 18 kilometers apart from one from another. If they go along the road, then in 1 hour, they can be in this situation. This is one solution. They can be in this situation. They can be in this situation and also in, I'm sorry, oops, in this situation. Okay, so those are 4 answers for the second problem when we are going along the road. Now, when we are not thinking about going along the road, then we can go in any direction. And if you think about this problem, proving that all these distances are between 6 and 30 is not such an easy task for students. So who can solve those problems? The most complex problems are going to excelling students. I will not tell gifted because actually we're not identifying in heterogeneous classes who are the gifted, but when we're looking at the class, this is an asterisk task that we suggest only excelling students to cope with and arrive at the inequality. So again, PowerPoint. So what I wanted to present here, that first of all, teachers are really excited about those tasks. We have applets to almost all the tasks which are open, not only movement tasks. We have tasks with graphs and coloring tasks and calculating tasks and mean score for test tasks. So teachers really start using them, and we have more than 1,000, this year, more than 1,000 lessons were conducted with those math key problems. So now I'm going to another study, which I conducted with Chaim El-Grabli. He just completed his dissertation. This is part of his PhD dissertation. When we worked with investigation tasks, and the goal of the study was to see how students, university students or school students, some of whom are members of Mathematics Olympiad team, and some of them are majors, excelling majors in the university courses, how they posed problems through investigation. What does it mean, posing problems through investigation? It means that they are presented with a figure, with a problem. They investigate this figure. Here you can see this I'm sorry. They have a figure, they have a problem. And what we're doing in those tasks, we remove a condition. Instead of saying prove that, we just give those conditions and say find at least two non-trivial properties of this figure through investigation in dynamic geometry, and they have opportunity to work on this in dynamic geometry, and formulate new problems and solve them. So the condition is not only posing new problems, but also solving what you posed. What are the differences? We asked what are the differences between a problem posing through investigation by mathematical Olympiads or mathematical majors, and what are the mutual relationships between proof skills and creativity components of this problem posing through investigation. So this is an excerpt, an example of excerpt, and you also can find this in the journal. But what was interesting that, and this is one of the MO participants that I marked here with the color, they looked all the time for something interesting for them. They could cancel some discovery or some problem that they could find or formulate because it's not so interesting. So we recorded all what they said during the interview, but you can see that actually through auxiliary construction and through thinking about proving previous properties, previously discovered properties, they arrived at very interesting properties that we didn't think about. So what I can say you that the solution space that Marian mentioned earlier, the solution space for this problem posing space, the space of posed problems included overall 309 problems. That was scored for creativity, for originality, for flexibility, for fluency, for complexity, and for complexity of auxiliary constructions. So we analyzed all those things when students, the two groups were working with dynamic geometry, and we could follow those constructions and those posed problems and their solutions. Also, we can analyze whether they could solve all the solutions. So this is the resulting, this is the resulting figure at which this MO expert, Dave, arrived. Okay, so you can see that complexity, they were performing this investigation about an hour and a half. So, and they were excited about this activity. Now, mathematical majors were trained to perform those investigations, and they performed investigations contrary to mathematical Olympiad solvers. They performed them after training to solve the investigation tasks. So you can see, I will not going into scoring scheme, but you can see that they found 12 different discoveries or formulated 12 different problems, and actually proved all of the problems that except of one of them. He just didn't find it interesting to prove and said that it's obvious. So he has very high flexibility. You can see that 7 of the problems that he formulated were totally different. He has 6 very original problems which other people didn't think about. And overall, his creativity was very high. Also, you can see that he performed 7 very complex auxiliary constructions, and the problems that he formulated also were very complex. On the contrary, this is the best participant from mathematical majors. So he formulated 7 new problems on the same task. And this is his resulting figure. He didn't prove all the discoveries, didn't succeed to prove all the discoveries. He actually, his constructions were also, some of them were very complex, but not all of them. And his creativity score was lower as originality and flexibility. So when we compared, and you can see these resulting figures for mathematical major, this is the best result for mathematical majors, and this is the best result for mathematical Olympiad participant. You can see that on all the criteria that we examined, both on proof skills and creativity components, those posed problems, the Olympiad participants were much better, much better than mathematical majors. So this was used as a research tool and as to see whether this mathematical expertise of different kinds, and actually we can say that in many studies, if you analyze studies on mathematically gifted, those mathematical majors in many studies, in neuroscience, for example, are considered as mathematically gifted if they are studying mathematical courses, and most of the mathematical courses that they had scores above 95. So many people would say, okay, they are also gifted. So mathematical Olympiads, training in mathematical Olympiads is very different, and the students chosen there are not only those who can get very high scores in university courses, and we can see that they are much more creative, and creativity is really related to experience of training for mathematical Olympiads. And problem-solving expertise at a high level significantly influence quality of problem posing through investigation. And we actually formulated something that is tricky. I don't know whether everybody will like this sentence. University mathematics courses do not develop creative mathematical abilities and skills. I don't want to tell all the courses, because now in another PhD study, we see that some of the courses really depends on the professor of mathematics who are teaching course. So for some professors, we find very high correlation with mathematical creativity in mathematical scores, but in a small number. I have to tell that only a small number of these courses are directed at development of creativity. Now, the title of the task of the lecture, as I promised, is the differences in relationships between open start and open end problems. Investigation task is a very special task, which is also open end and open start, like problem posing task and like sorting tasks. They are very uncommon for mathematical lessons, both in regular classes and in classes for gifted. And mathematical Olympiad participants of our study, they said that first time in their life, they actually posed problems. The activity was directed at posing problems, but this is the part of their solution of the problems, that they are formulating new, probably more simple tasks to solve a very complex task. So this problem posing is inherent for solving the problems. That's why we think they could produce such a rich collection of tasks and very original tasks. Now, when we think about what can we do with all those open tasks, then some of the tasks allow evaluation of creativity and some are not. And I want to tell here a word about mathematical multiple outcomes task, like this movement task. It's not that it's open, and I think about it a lot during last time. The problems have multiple solutions, but they're not open, and I don't know why they're called open now. I struggle with this notion, because the answer is inequality, or answer is a set of numbers, or the answer is a set of geometric figures, or it's a set of geometric figures with common feature. So it's not that it's that open, even it has infinite number of solutions. If you don't provide all the answers for such an open outcome task, then it's incomplete, and we now evaluating completeness of the task. So we find it difficult to evaluate creativity with a task when you have very specific answer, which is a segment or a set. And one more comment. When we ask teachers to pose open task, then it's like squared open task, because they cope with opening regular problems to pose open tasks. So they perform on open task to create open task. Thank you very much for your attention.